welcome to Astronomy in Space. In this month's program we take a look at NASA's latest moon mission, the Lunar Atmosphere and Dust Environment Explorer, LADEE, which is set for launch on September the 6th. We also view the planet Jupiter, which is now attracting attention from amateur astronomers, including how to best observe the cloud features and carry out transfer measurements over the coming months. But first, let's take a look at the highlights of the September night sky. The autumn equinox occurs on September the 22nd, when day and night are equal all over the world except the polar regions. The nights are continuing to get longer, with more time for stargazing. The sun sets at 8:47 p.m. at the beginning of the month and 7:40 p.m. on September the 30th. The average sunrise time being 07:35 a.m. The planet Mercury has now moved away from the Sun. However, it is very difficult to see low down in the eastern sky shortly before sunrise from September the 11th. The planet shines at magnitude -0.3 and is only 3.5 degrees from the Sun, and its altitude declines still further by the end of the month. As a signpost of the planet, the slender crescent moon will be south of Mercury on the morning of the 6th of September. The planet Mercury lies in the zodiacal constellation of Virgo, along with the brighter planets Venus and Saturn. At the beginning of the month, the planet Venus is visible 5.5 degrees above the southwestern horizon after sunset, shining at magnitude -4.0, and its gibbous phase is visible in small telescopes. Venus will be 1.3 degrees north of the crescent moon on September the 8th, which is also the occasion when the moon will occult the planet as seen from a small island in the North Pacific Ocean, near the Marshall Islands. Venus is now moving across the sky in a retrograde path out of the constellation of Virgo into Libra, the scales. At the beginning of the month, Mars rises at 03:39 a.m. over 4.5 hours before the Sun. Shining at magnitude +1.64, the planet can be seen above the eastern horizon in the constellation of Cancer, the Crab. On September the 2nd, Mars will be 6.8 degrees north of the Moon, making an ideal photo opportunity. The angular diameter of Mars is small, so quite a large telescope is needed to see any detail. However, this is an exciting time for astrophotographers, as the planet passes through the star field of Messier 44, the Beehive Open star cluster, from the 8th until the 12th of September. Mars will be in the middle of M44 on the morning of September the 9th. A pair of 10x50 binoculars will show this lovely open star cluster really well. M44 covers an area of 95 arc minutes and contains over 40 bright stars of about magnitude +3.7. According to measurements by the European Space Agency's astrometry satellite, Hipparcos, the cluster is 577 light-years distant, and its age is estimated at about 730 million years. Shining at magnitude -2.06, the planet Jupiter can be seen as a bright yellow-like star in the southeastern sky near the middle of the constellation of Gemini, the Twins. At the beginning of September, the planet rises soon after 2 a.m, and by the end of the month, Jupiter will rise at midnight 30. The planet also gets brighter as it heads towards opposition on the 5th of January 2014. Therefore, there is a lot to observe on the planet over the coming weeks with small telescopes, while a pair of binoculars will show the planet's 4 bright moons as they change positions around the planet. I'll have more to say about Jupiter later in the program. The ring planet Saturn is still visible in the southwestern sky after sunset, shining at magnitude +0.69, and lies in the constellation of Virgo. At the beginning of the month, the planet sets at 1 hour 45 minutes after the Sun. However, the planet is now rapidly descending into the glare of the dusk sky. There is still time to view the planet's splendid rings in small telescopes until the latter half of the month. Saturn sets less than 5 minutes after the Sun on September the 30th and reaches superior conjunction on October the 25th. Saturn will be 3.3 degrees north of the Moon on the 9th of September, and the ring planet will be 3.8 degrees north of Venus on September the 20th, making ideal photo opportunities. Now, what about the Moon? New Moon appears on the 5th of September, the first quarter Moon is on the 12th of September, full Moon occurs on the 19th of September, and last quarter is on September the 27th. The Moon will occult the bright star Spica on September the 8th, as seen by Canadian amateur astronomers in New Brunswick and Nova Scotia. The event is not visible from the UK, as it takes place at 3:30 p.m. in the afternoon. NASA will launch its new spacecraft, the Lunar Atmosphere and Dust Environment Explorer, LADEE, on September the 6th from Wallops Island, Virginia. After launch, LADEE will take 30 days to travel towards the Moon, where it will be placed into a circular 50 kilometers, 31 miles above the lunar surface. The spacecraft will take 113 minutes to complete each orbit of the Moon, and the mission is expected to last up to 9 months. The science payload consists of a neutral mass spectrometer, which will perform in situ measurements of atmospheric species, and an ultraviolet visual spectrometer, which will measure both the dust and atmosphere. LADEE also carries a technology demonstration payload for testing an optical communication system. The Lunar Laser Com demo will use a laser to transmit and receive data as pulses of light, much the same as data is transferred in a fibre optic cable, to 3 ground stations. This method of communication has the potential to provide 6 times the rate of data return from both LADEE and future missions. The technology is a direct predecessor to NASA's Laser Communications Data Relay satellite, due to launch in 2017. Here are LADEE Project Manager Butler Hine, LADEE Program Scientist Sarah Noble, and Don Cornwell, Mission Manager Lunar Laser Communications, to tell us more about the highlights of the mission.
One of the things that is a first is we're trying out a modular spacecraft bus that is not designed for a single mission. It's designed in a modular fashion so you can use it for different missions by combining it in different ways. If you bring up my first slide, you can see the architecture. You can see the individual modules. There's a top module which contains most of the electronics and power switching devices on the observatory. There's a payload module where the 2 biggest instruments are located on opposite sides for balance. It also has our reaction wheels for fine pointing control. There's an extension module, and within that is the propulsion module. You can put different types of propulsion modules in this spacecraft architecture, but in this case we're using a proven commercial design from Space Systems Loral that is a biprop system, meaning it has 2 fuel tanks and 2 oxidizer tanks, and it's a pressurized system. Some things to notice about this spacecraft design is it does not have the wings that you normally see on a lot of modern designs. Those wings give you a lot of power. They're deployed after launch, but they require that you always point at the sun, because it's very bad for a spacecraft to lose power, obviously. So you always want to be pointing at the sun. One of the characteristics of this design that you can see is that it has solar panels all over the spacecraft. What that means is the spacecraft can be in pretty much any attitude and still generate power. That means it's a very inherently safe design. It's very difficult for this spacecraft to ever get in a condition that it can't wake up from. If you go to the next slide, what you'll see is this is what LADEE looks like right now. When we put the spacecraft together in this modular fashion, it was done in a way to lower the cost of production. One of the characteristics is this carbon composite frame that the spacecraft is built of to be very strong and very lightweight. The other thing we did was take advantage of any modern electronics, any modern devices that were designed for space, rather than designing things from scratch. So this is think of it as a bus that you can use for a multitude of purposes. I'm very happy that we got the chance to fly this on the first time for a lunar mission, because that really proves out some of the characteristics of the bus. After we put the bus together, we went through a lot of testing. You really want a spacecraft to experience the rigors of space before you fly it. So we shook it, we blasted it with loud noises, we simulated the shock when it separates from the launch vehicle. We put it in a hard vacuum chamber, we baked it to high temperatures, cooled it to very low temperatures. tested all of its communications equipment with the actual relay satellites that we're going to be using. We did all this in preparation to shipping it to the range. It's been at the range this summer. We just finished doing all the spin balancing, all the fueling of the spacecraft, and now it's encapsulated with the fifth stage, the upper stage. It's encapsulated in the nose cone of the rocket. This weekend, we plan to roll it out and stack it on the rest of the launch vehicle, which is already stacked at the pad. If you go to the last animation, you can see what it looks like in flight. This is an animation showing what you would see if you were outside the spacecraft looking at it on the way to the moon. There's a couple of interesting things about how we get to the moon. If you're my generation, you remember the Apollo era. They got to the moon in a classic figure-8 pattern. It's a very efficient way of getting to the moon. It takes a lot of fuel, however. And because of trying to optimize the amount of fuel that we have for the science mission, we go in a different way. We launch from Wallops, and then we go into these elliptic orbits around the Earth. We take a couple of passes around the Earth, and each pass we get higher and higher until finally on the third pass, we're hanging out there in space right around where the moon's going to come by. It swings by, whips us around behind it, and then once we come out from behind the moon, we do a big braking burn with our main engine that you can see there. That braking burn is what captures us around the moon. We spend about 30 days commissioning the science instruments. We do the optical comm experiment during that time, and then we drop down into the low science orbit. The low science orbit is about 30 to 70 to 90 miles above the lunar surface. It's very low. And when you're that low above the moon, the lumpy gravity field requires a lot of fuel to maintain. So we drop down into that orbit, do our active science where we're flying in and out of the light-dark terminators around the moon. And then at the end of the mission, we terminate the mission by intentionally crashing into the lunar surface, taking science on the way down. And now I'd like Sarah to talk about the science aspects of the mission.
Thanks, Butler. So as you've heard, LADEE has two main science goals: to understand the lunar atmosphere as well as the dust environment around the moon. And I think sometimes people are a little taken aback when we start talking about the lunar atmosphere because, right, we were told in school that the moon doesn't have an atmosphere. It does. It's really, really thin. It's so thin that the individual molecules that make up the atmosphere are so few and far between that they don't interact with each other. They never collide. A collisionless environment, which is something we call an exosphere. If I can get my first graphic, the Earth actually has an exosphere as well, but you actually have to get out past where the International Space Station orbits before you get to this condition that we can consider an exosphere. On the moon, that actually happens right at the surface. So the term we use for this class of atmosphere is a surface boundary exosphere. And it's not just the moon. Surface boundary exospheres turn out to be the most common type of atmosphere we have in the solar system. So Mercury, a lot of the moons of other planets, even some large asteroids are big enough to have a surface boundary exosphere. And it's a class of atmosphere we actually don't know that much about. So it turns out the moon is actually a really convenient place to go and learn about this really common type of atmosphere. It's also a really good time for us to go and explore the lunar exosphere. Because it's so delicate and thin, it's easily disturbed by things like spacecraft landings. Things have been relatively quiet around the moon in terms of landings for the last few decades, but it's not going to stay that way for long. There's actually a number of countries, a number of private companies that are planning landings to the moon in the upcoming years. So now is a really good time to go and take a look at it while it's still in its sort of pristine, natural state. The second science goal is to look at the dust environment around the room. And if I can get the second graphic. We've actually had questions about the dust environment since even before Apollo. If you look at the image on the left here from the Surveyor 7 mission, it captured something right along the horizon just before sunrise, this strange glow that we think might be due to dust scattering sunlight in the atmosphere. The Apollo astronauts actually saw something similar thing too. If you can see on the right side is a sketch from Apollo 17 astronaut Gene Cernan's notebook, where he saw not just that horizon glow, but also these things he saw streaming high up into the atmosphere, something he called streamers. We think this also might be due to very tiny particles of dust getting lofted tens of kilometers up into the sky. So this is finally an opportunity that we can go and solve this mystery that has been puzzling scientists for almost 50 years. So we're very excited to finally get an opportunity to understand what the dust environment is going to be like around the moon. So we have three science instruments, if I can get my last graphic, on our science payload in order to explore these questions. The first is the Lunar Dust Experiment. It is designed and built by the University of Colorado, and it will actually analyze individual dust grains as they approach the spacecraft. The second is a neutral mass spectrometer designed and built by NASA Goddard. It will actually look at the composition of the various molecules in the atmosphere as well as their distribution over the course of a lunar day. The third and final instrument is an ultraviolet spectrometer brought to us by the NASA Ames. And it's not the first spectrometer that we've sent to the moon. We've actually sent a number of spectrometers. Usually, though, when we send a spectrometer, it's looking down at the surface of the moon so that we can understand the mineralogy of the rocks at the surface. This spectrometer will actually look sideways, just above the lunar surface, so that we can go through the atmosphere and analyze what is in the atmosphere and the dust environment. So those are our 3 science payload. There is a 4th payload, as has been mentioned, and I'm going to turn it over to Don to introduce us to that one.
Thank you, Sarah. And I'd also like to thank the Science Mission Directorate and the LADEE mission for giving us a ride to the moon, our technology demonstration, where we're going to use laser communications to demonstrate at least 6 times more data rate from the moon than we can do with a radio system with half the weight and also 25% less power. And my first graphic is up, and if you can see that, it actually gives a good illustration of what the concept of the mission is. You can see the LADEE spacecraft on the left and our instrument at the bottom, which is a little small telescope. And it will basically exchange laser beams between the Earth and the moon to a new type of ground station. So with this system here, we plan to be, or we will be NASA's first high-rate two-way laser communications demonstration riding along with LADEE to the moon. The next slide, please. So NASA has a need for faster download speeds for data from space, and it grows every day just like it does for the rest of us at home and also at work. We'd like to be able to send high-resolution images and movies in 3D even from satellites that not only orbit the Earth, but also from probes that will go to the moon and beyond. So communicating with radio waves has served us well for the last 50 years, but we now have the technology to use light waves to communicate even more data. Light waves are much shorter in wavelength than radio waves, as you can see in the figure, and that allows us to use smaller transmitters and smaller receivers. For example, in the figure, you can see that a typical radio dish is on the left-hand side, and our ground terminal is on the right-hand side. And if you can, on the animation, please play the animation. While we send 6 times more data and use less power, we're actually a bunch smaller, quite a bit smaller, as you can see. So faster bandwidth, smaller size, and less power needed. The next slide, please. So this is an animation of our actual mission concept right here. We have 3 ground stations, and then you can see the LADEE spacecraft, and we've highlighted in bright blue our space terminal. So a beam from the ground, from one of the ground stations, will scan around the moon to where we expect LADEE to be. And when LADEE sees that beam go by, it will send its own signal back down to the ground station so that the 2 systems can lock up and acquire each other. Once the 2 systems are locked and acquired, then we can send tens of megabits of data per second from the Earth up to the moon. And similarly, we can send hundreds of megabits per second from the moon and on LADEE down to the Earth. And so we hope that successfully demonstrating this over and over again during the LADEE mission under all the conditions that you can see in the atmosphere and day and night and moon behind you and such will build the confidence for future NASA missions to use this technology for their communications systems. Finally, I'd like to point out that the MIT Lincoln Laboratory built our flight terminal and also built our primary ground terminal, and we also have partners. NASA's JPL has built a ground station for us in Wrightwood, California. And then finally, the European Space Agency has also built a ground station in Tenerife, Spain. And we're looking forward to collaborating with everyone and LADEE.
On the night of August the 14th, Japanese amateur astronomer Koichi Ikgak discovered a magnitude 6.8 nova in the constellation of Delphinus. Some have suggested that the star Tycho 1643-21041 is the star responsible. However, the fainter of 2 catalogue stars close by seems to be more likely candidate. The Sinberg catalogue gives its magnitude as plus 17.20, BV 0.48. Since then, the nova has brightened to magnitude plus 4.5 on August the 16th, so that it was visible to the naked eye, and within easy range of a pair of binoculars. This places Nova Del 2013 in the top 30 brightest nova in recorded history. The nova then began to slowly fade from magnitude plus 4.8 on the 18th to plus 5.2 on the 20th. So far, it appears Nova Del 2013 is a slow nova, type NB in BSX. By definition, it takes 150 days or more for a slow nova to fade by 3 magnitudes. This means that the star will still be at magnitude plus 8.2 on January the 20th, 2014. The light curve of Nova Del 2013 indicates that it is of a classical type with hydrogen alpha and beta in its spectra. So what does this mean? A nova is a cataclysmic nuclear explosion in a white dwarf star. In a binary star system, if the 2 stars are close enough, material from one star can be pulled off the companion star's surface and onto the white dwarf. The destruction of the star is caused by the accretion of hydrogen onto the surface of the star, which ignites and starts a nuclear fusion in a runaway manner. Nova Del Finis 2013 was preceded 45 years ago by Nova Del 1967F, which was discovered as a star of visual magnitude plus 5.6 by G.E.D. Alcock in Peterborough, England, on the evening of July the 8th. This is also a slow nova, and its light curve since then has fluctuated in various ways. Pre-discovery observations show that the nova increased rapidly in brightness on June the 30th, 1976. The nova then slowly increased in brightness to plus 5.4 on July the 26th, before fading and fluctuating around magnitude plus 9 for quite some time. It is still visible today as a magnitude plus 12 object. So expect the unexpected with Nova Del 2013 in the coming weeks and months. Now on to our main theme. Our solar system is made up of the Sun in the centre. Then in order of distance we come to the 4 rocky planets, Mercury, Venus, Earth and Mars. This is followed by a wide gap filled with over 3,000 chunks of debris called the asteroid belt, and then we come to the 4 giant gaseous planets, Jupiter, Saturn, Uranus and Neptune. Jupiter is the giant of the solar system and is the 5th planet in order of distance from the Sun. It is a gas giant with a mass 1,000th that of the Sun, which is 2.5 times the mass of all the other planets of the solar system combined. Jupiter is classified as a gas giant along with Saturn, Uranus and Neptune. Together these 4 planets are sometimes referred to as the Jovian or outer planets. In terms of gravity, an average-sized man on Earth would weigh twice his body weight on Jupiter. The planet was known by astronomers of ancient times and was associated with the mythology and religious beliefs of many cultures. The Romans named the planet after the Roman god Jupiter. Telescopically, it shows a yellowish, decidedly flattened disk upon which various markings may be seen. Surrounding Jupiter is a faint planetary ring system and a powerful magnetosphere, 450 million miles wide. There are also at least 67 moons, including the 4 large moons that were first discovered by Galilei in 1610. Ganymede, the largest of these moons, has a diameter greater than that of the planet Mercury. Jupiter has been explored on several occasions by robotic spacecraft, most notably during the early Pioneer and Voyager flyby missions and later by the Galileo orbiter. The most recent probe to visit Jupiter was the Pluto-bound New Horizons spacecraft in late February 2007. The probe used the gravity from Jupiter to increase its speed, and future targets for exploration in the Jovian system include the possible ice-covered liquid ocean on the moon Europa. The planet's diameter, as measured through the equator, is 88,700 miles, but the polar diameter is several thousand miles less, so that the flattening is very much greater than for the Earth, where the difference between the polar and equatorial diameters amounts to only 26 miles. In its outer layers, at least, it is made up of gas. Also, it is spinning quickly on its axis. The Jovian day amounts to less than 10 hours. The planet's shape is therefore that of an oblate spheroid, that is to say, it possesses a slight but noticeable bulge around the equator. The same bulge effect is seen with the other giant planets, Saturn, Uranus and Neptune. However, Jupiter is much the easiest to observe. Not only is it much the largest of the four, but it is also the closest to us, even though its mean distance from the Sun is 483 million miles, and its revolution period is as much as 11.86 Earth years. Jupiter does not rotate in the manner of a solid body. Various zones and various specific surface features have periods of their own. Amateur astronomers have provided much of the information about the rotation periods, and work of this kind is still being carried out with valuable results. When viewed from the Earth, Jupiter can reach an apparent magnitude of -2.94, bright enough to cast shadows, and making it on average the third brightest object in the night sky, after the Moon and Venus. The main features are the belts and spots. The cloud belts, which stretch across the disk, are visible with small telescopes. There are several of them, of which the most prominent at the moment are those to either side of the Jovian equator, the North Equatorial and the South Equatorial belts, and the South Temperate belt in rather higher latitude. Throughout 1966 and early 1967, the South Equatorial belt was obviously double. There are, in addition, various other belts. It has been found that the equatorial region of Jupiter, that is to say the region lying between the two equatorial belts, has a rotation period of only about 9 hours 51 minutes, while the rest of the planet has an average period about 5 minutes longer. These two zones are known as System 1 and System 2, respectively. It seems that we are dealing with a quick-flowing equatorial current. There are also currents in other zones, and occasionally a small creature may be seen speeding around at a truly remarkable rate. The interactions of these conflicting circulation patterns cause storms and turbulence. Wind speeds of 100 meters a second, 223 miles an hour, are common in zonal jets. The zones have been observed to vary in width, colour and intensity from year to year, but they have remained sufficiently stable for astronomers to give them identifying designations. The cloud layer is only about 50 kilometres, 31 miles deep, and consists of at least 2 decks of clouds, a thick lower deck and a thinner, clearer region. There may also be a thin layer of water clouds underlying the ammonia layer, as evidenced by flashes of lightning detected in the atmosphere of Jupiter. As Jupiter spins, the various surface features seem to be carried across the disk from one side to the other. When a feature reaches the central meridian, as seen from the Earth, it is said to be in transit. Its longitude on Jupiter can then be worked out from some basic tables, and clearly successive transit observations will give the time taken for that particular feature to complete one rotation. It is by transit observations of this sort that the rotation zones of Jupiter have been measured with such accuracy. While major features such as belts and equatorial dark projections can be seen with an 8 cm 3-inch telescope, satisfactory observations require a telescope of aperture at least 15 cm 6 inches. Most people like to draw what they see, and this is a skill that takes some practice to develop. Good drawings are welcomed as illustrations of the general appearance of the planet, and may occasionally be useful as records of special events. The standard size for a disk drawing is 64 by 60 millimeters, about 2.5 inches. A more advanced option is to develop one style of drawing, or even colour painting, so as to combine observational accuracy with artistic quality. Another option is to make strip maps, cylindrical projection maps of parts of the entire planet, one or more times during their apparition. This gives a valuable overview of the pattern and belts and spots around the planet. Useful longitude measurements of the spots can be made by timing their transits. This does not require any special equipment. One just estimates the time at which the spot crosses the central line of the disk, the central meridian. The observer should give the transit time to the nearest minute, which corresponds to 0.6 degrees of rotation in longitude, and calculate L1 and L2 from the tables of the BAA handbook. Some observers have made intensity estimates for belts and zones through red and blue filters, and this should also be a means of recording colour. A project for an experienced observer could be to systematically compare visual colour impressions. Visual red minus blue estimates, and colour impressions on processed CCD images, and to calibrate them against absolute intensity measurements and multi-filter CCD images. Estimates of the intensity, darkness of belts and zones can be made numerically on a scale from O brightness to 10 black sky. Observers who make colour or intensity estimates should tabulate and average them for the whole apparition and note any insignificant changes. The transits, shadow transits, eclipses and occultations of the 4 Galilean satellites are among the most striking phenomena that a beginner can observe, although observations are not likely to have any scientific significance. Observers may like to make accurate drawings of these phenomena, especially when several are occurring at once. Every 6 years, the satellites occult and eclipse one another, and it is interesting to plot visual light curves of the mutual eclipses. There is no real difficulty in deciding which is the central meridian, because the planet's polar flattening is so obvious. Incidentally, the angle made by the planet's equator compared with its orbital plane is only about 3 degrees, as against the well-known 23.5 degrees for the Earth. Jupiter goes around the Sun in an almost upright position, and so there are no true seasons there. However, the presence of or absence of seasonal effects is not important, because the temperature is always very low. Much the most famous feature on Jupiter is a great red spot, a giant storm that is known to have existed since at least the 17th century, when it was first seen by telescope. Therefore, it has been under observation for more than 300 years, and has attracted a great deal of attention. It is a large object, 30,000 miles long at its greatest extent, and with a surface area greater than that of the Earth. Moreover, it really is reddish, and this colour has been very pronounced during the opening weeks of August. The spot rotates counterclockwise with a period of about 6 days. The Great Red Spot's dimensions are 14 to 24,000 miles by 7 to 8,000 miles. It is therefore large enough to contain 2 or 3 planets of Earth's diameter. The maximum altitude of this spot is about 8 kilometres, 5 miles above the surrounding cloud tops. There are some years when the red spot cannot be seen at all, though usually its hollow remains traceable. At other oppositions, the spot dominates the southern hemisphere of the planet. Although transits occur daily, look out for the Great Red Spot transiting the central meridian of Jupiter on September the 5th at midnight 35 am and September the 17th at midnight 31 am. All times are in UT, the time system usually used for timing astronomical events. Between 1901 and 1941, there was a dark feature in much the same latitude as a red spot, known as the South Tropical Disturbance. Since 1941, it has not been seen, but a disturbance of the same kind was found in the autumn of 1966 by Robert Moseley and was confirmed by Sir Patrick Moore. It did not last for long and had vanished by the new year, but it may revive at any time. Jupiter is always doing the unexpected, and one can never tell what is likely to happen next. Jupiter is also a source of radio waves. All the evidence shows that Jupiter must have a powerful magnetic field, and that the radio emissions are closely bound up with what we call the planet's magnetosphere. For Jupiter, this is colossal. It stretches 450 million miles out to the orbit of Saturn. Another unexpected discovery was that the radio bursts from Jupiter are connected with the position in orbit of the innermost large satellite, Io. Therefore, Io has an effect upon the Jovian ionosphere, and the same may be true of the much smaller fifth satellite, Almathea, which lies closest to the planet. The 4 main moons are visible with any small telescope, or even with good binoculars. They were discovered in 1609, 10 by Galileo, and perhaps slightly earlier by Marius. 2 of them, Ganymede and Callisto, are considerably larger than our moon, and are probably larger than the planet Mercury, though not so massive. Of the others, Io is about the size of our moon, Europa is rather smaller. It is a simple matter of plotting their positions each night as they move around Jupiter. Identification is a different matter. However, many astronomy magazines, such as that of the Sky at Night, publish tables which makes this easy. Surface details can be seen with giant telescopes, but not with average-sized instruments. Anyone who records surface markings on, say, Ganymede with a modest telescope is simply drawing upon his imagination. The owner of a small telescope may, however, learn a great deal by studying the movements of the four large satellites. Sometimes there are transits when a satellite passes in front of a disk. Note that the meaning of the word transit in this connection is quite different from that of a surface feature transit. Then too, a satellite may be hidden or occulted by the planet, or be eclipsed by Jupiter's shadow. Timings of these satellite phenomena are of value, always provided they are really accurate. The most interesting of the other satellites is Almathea, which was discovered by E. Barnard in 1892. It is closer in than any of the other four Galileans, but it is below 200 miles in diameter and cannot be seen except with large telescopes. Altogether, Jupiter's satellite family includes 67 members. The outer 7 are very small and are probably captive minor planets rather than bona fide satellites. 4 of them have retrograde motion, that is to say they move around Jupiter the wrong way, and they are so remote from the planet that their orbits are not even approximately circular. It is probable that additional faint satellites exist and may be discovered in the future. In every way, Jupiter is a fascinating world. It is also the object which offers the greatest scope to the amateur astronomer who is reasonably well equipped. Its surface is always changing, and one can never tell what each new apparition will bring forth, so that there is plenty to be done. Even those who have no equipment other than binoculars can take an interest in Jupiter. Well, that's all we have time for this month. Thank you for watching. Until next time, goodbye for now.